Want to start? Okay, so let's get started. What I'm going to do today is just first finish a couple of slides that were remaining from last time, and then we'll start talking about a new topic which is going to be processes, threads, scheduling, virtualization. So it's a topic will span several classes, but we will cover a sequence of different things in there. Okay, and first of which we will start talking about today. But let's go back to what we were talking last time. Okay, so last time I did a very high level introduction of distributed systems architecture. We saw a whole slew of high level architectures which included bulletin board architecture, client server architecture, whole slew of them, multi-tiered architectures and so on. And towards the end of the class we were talking about peer-to-peer systems. Okay, I introduced the notion of structured peer-to-peer systems. We talked about unstructured peer-to-peer systems, and we were discussing Skype and super peers and so on, which is when we ran out of time. So we'll just continue from that point on. Okay, so yet another kind of a peer-to-peer system is BitTorrent, which I presume all of you have heard of or may have used in some shape or form. Okay. Now BitTorrent is not just a peer-to-peer system, but it has some other interesting features that I'll talk about, and it falls under the category of collaborative distributed systems. Okay, and I'll explain what that means, but let's first talk about what BitTorrent does that makes it different from other peer-to-peer systems. Okay, so in BitTorrent there are two or three different things that you need to keep in mind. The first thing is BitTorrent is a P2P system for distributing large amounts of content. Okay? One of the key features of BitTorrent is this notion of parallel downloads. Okay? So each peer will try, when it tries to fetch let's say a large file, it will connect to multiple other peers that have that content and try to download different parts of that file in parallel. Okay. Parallel downloads give you a speed up over sequential download, especially when there is a lot of content, because the bandwidth to any one peer may be small. Okay, but if you are on a higher speed connection, connecting to multiple peers will allow you to exploit parallel download bandwidth and get you that piece of content faster. Okay. So the first thing is it allows you to do parallel downloads. Essentially a large file, okay, is partitioned into smaller pieces called chunks. Chunks are replicated across peers. Okay, and when you need to download a file, you find some subset of the peers that have that content, and you try to get different chunks from different peers in parallel. Okay, as you get downloading one chunk, you find a peer and another peer that has the next piece of that file, next chunk, and start downloading it from. Okay, and the degree of parallelism can be varied based on many factors, such as the amount of bandwidth your machine has going to the internet and things like that. Okay? That's the first thing that is interesting about BitTorrent. Okay? The second interesting thing within BitTorrent is the notion of incentives, which is why you have this notion of collaborative distributed system. Okay? Now one of the problems that designers of P2P systems found was that there were many users who wanted to be part of the system to download content from others. Okay? But once they were done downloading content, they would just switch off the P2P client and not share that content or other content with others, because they would say that my job is done, I downloaded whatever I was interested in, so now I'm going to go turn this client off and do other things. Okay? Which essentially means that the users are selfish. They try to do what they want, but they are not contributing resources to the system, which is sharing that content so that others can download it. Okay? Now BitTorrent has explicit incentives built into it, which tracks the amount of content you have shared with others. Okay? And if you are downloading more and uploading less, it will slow you down in the future for future downloads. Okay, so it's going to throttle your bandwidth. So regardless of how many resources you might have, it will say you are not sharing enough, so you pay a penalty for that by getting a slower download. Okay, so it's essentially encouraging you to be part of the system and share the content that you downloaded with others. Okay, so basically you want to maintain a good upload to download ratio, which means that for any piece that you download from other peers, you want to also upload, or upload meaning you let others download from you. Okay, so this incentive is actually built into BitTorrent. Okay, and this incentive mechanism has actually been studied independent of BitTorrent, but it came out of BitTorrent, which is how do you encourage users who have selfish intent to participate in a larger system and contribute resources. What incentives make sense? Okay. In this case, there is no monetary incentive. It is just that your performance will be slowed down if you do not contribute resources back to the system. Okay, so that's an interesting aspect. So it is forcing this property called altruism, where you want to be altruistic, not selfish. Okay, so those are two key features. One is parallel downloads, the other is built-in incentive. Okay, so now with that in mind, let's look at how BitTorrent works. It is shown in this picture. Okay, so essentially for any piece of content that you want to download, you have to first go and get what is called a torrent file. Okay, torrents could be published on the internet, or they can be shared in any other mechanism that you want. Let's say you go to a website and download a torrent file, which has more information on how you can go and download that piece of content. Okay, so you will basically go to a web page and download a torrent file. Okay. Now once you download a torrent file, it has information in it, and the most important piece of information is it has what is called a list of tracker nodes. Okay. Trackers are essentially nodes that have that might either point you to the content or have the content themselves. Okay. So then you can connect. So as you will see that there is a torrent file which is a reference to the tracker. The tracker will have a list of nodes. It's tracking which nodes are part of the system that have this content already. Okay. Trackers might themselves have the content as well, but they at least have to have an index of who has the content. Okay. So you will basically connect to the tracker. The tracker will say here are n nodes that have that content, that are sharing it. Remember that this file is partitioned into chunks. Okay. So each node has at least some number of chunks, if not all the chunks of that file. Okay. And then this client will then take the list of nodes and say, if you say degree of parallelism is k, we will connect to k of those nodes and try to download the first k chunks. Okay. As each chunk has downloaded, then you will repeat this. You might vary k as you see that there is more bandwidth or less bandwidth. So there are many mechanisms that will allow you to figure out the degree of parallelism. Okay. So you will put all of that together and then you will get your content. Okay, it will basically be downloaded in parallel. Okay, so that in a nutshell is what BitTorrent does. The interesting thing here is, unlike CORD or CAN or any of these other networks we saw, there is no overlay network of peer nodes that are part of a system. Okay, they are somewhat loosely disjoint. Each group of nodes have some pieces of content, and there are trackers that are tracking which nodes have which content, but it's not necessary that nodes are connected to one another in any overlay network form or in any topology. Unlike CORD, which had a ring topology, or unstructured network that had an arbitrary graph topology, there is no such topology here. Okay? But you still can have trackers and nodes that are part of the system. Each node can be pointed to from many trackers if it has many pieces of content. Okay, so that's how this system works. Are there any questions on this? Yes.
Is this system secure? Can I change the chunks of the files to different ones, but which basically is visible to clients like an actual file, like an actual chunk, but in reality?
Okay, question is the system secure? Can you actually change the content and pretend that they're chunks of the file and so on? So security is not part of the BitTorrent protocol. BitTorrent protocol just allows you to go download things and so on. Okay. If you want security on top, you will have to layer it by either encrypting the content or making sure the content has not been altered and so on. Okay, which also means that as it stands, it's very easy to inject malicious content in there and prevent you from sharing content by sending bad chunks and so on. Okay, so that's a whole different set of issues that are not part of the basic protocol. Yes, question there?
Is there like a single global tracker, or like there will be multiple trackers?
Okay, question is there a global tracker? So there is no such thing as a global tracker. It's a peer-to-peer system. There will be some subsets of some trackers, some number of trackers rather. Each of them may be tracking certain files. And then the torrent will tell you which trackers will have information about that file. There's one torrent for every file, or every file that is shared in the network. Okay? Yes?
How do companies like Comcast track that you're using P2P or downloading P2P files?
Okay, question is how do companies track that you're downloading peer-to-peer files and so on. So typically the way you figure out what kinds of applications are in use is by tracking the port numbers, the socket ID numbers, which tell you so every protocol will have some socket number or port IDs that it uses. So if you actually look at the packets and look at the source destination IP addresses and the port numbers, you can tell what kind of traffic it is. HTTP traffic is port 80, for example. So if you see port 80 traffic, you know that people are just doing HTTP. So you can do that. You can also look inside the packet and try to figure out if there are headers that tell you what kind of protocol it is. So there are many ways like that.
If we can change the port number to normal downloading file port number, so we can actually evade these issues, right?
So question is, can you change the port number to evade problems? So that is easier said than done, because there are, as I said, techniques that actually look inside the packet to see what the content is. Right, so your port number might allow you to evade the easy system, but if the system is more sophisticated, it will do what is called deep packet inspection and look inside the packet. So then if you see protocol information, which are part of the protocol, you can figure out what's going on. Okay, yes?
Are the trackers also like peers in the
Question is, are the trackers peers in the network? So trackers are just nodes that track other nodes. They can also be in content nodes that serve content. Okay, there's nothing that prevents them from doing that.
But who decides who a tracker is?
Who decides who a tracker is? So that's a interesting question. So that is how the system is set up. You can basically make a node saying I can track nodes and so on. Typically when a peer joins, you join as a content node. If you download a piece of content, you will get added to the tracker and you will become the n+1 node. To become a tracker requires you to do extra work. You don't just become a tracker. Okay. All right. So moving on. So the very last type of architecture we will talk about here before switching gears are what are called edge server systems. Okay, they are also called proxy server systems. Okay, so we talked about the client server architecture. Okay. Several times over the course of this next several lectures, we'll also see a different architecture, which is a client proxy server architecture. So there's a node called a proxy server that sits between the client and the actual server. Okay? The proxy acts as a proxy for the real server. It can do some of the work that the real server does, but not all of the work. Okay? Simple example of a proxy server is a proxy cache, where the server is caching some content from the real server, the origin server. Right? So typically in this architecture, and what is shown here is a complicated, looks more complicated than the system is actually. So you will see that there are clients and there are edge servers here, okay? And then there's the actual origin server there. Okay? But really what is going on is the clients actually talk to the edge servers talk to the origin server. The edge server is your proxy server. Okay? So proxies can do various interesting things. They can cache content, they can transcode content, they can provide other useful services. Okay? And we'll see many things that you can do with proxies. And one of those many things is what is called content distribution, which is basically you're using a lot of these edge servers to distribute content to end clients. Okay? And the assumption is, the key assumption that I forgot to mention is that proxies are typically closer to end clients than the actual servers. Okay? So if you connect to the proxy and the proxy is able to provide you whatever service you're requesting, you might get a lower latency or higher bandwidth than going to the actual server. That's the whole reason they exist to begin with. Okay? Proxies can also reduce the load on the server by servicing some requests locally rather than sending them to the server. Okay? So that's an example of having more than one servers, where you have the origin servers and you have proxy servers, and the proxy servers are typically deployed at the edges of the network, which is why they are called edge servers. Okay, so you will see in this case that content server might be far away, but here is another server that's at the edge of the network that may be closer to the client, which acts as a proxy. Okay, so we'll use the term edge server and proxy servers interchangeably. Okay, so keep this in mind. We will come back to it. We are going to have some more detailed discussions of content distribution and web caching and many other kinds of proxies further on in this course. Okay. Oh, there's one more system that I forgot to mention. So the one last architecture that I want to mention here are what are called self-managing architectures or autonomic architectures. Okay. So in this case, so this is a traditional distributed system, but one that can make autonomic decisions. Okay, so these are also called self-star system, where you are self-managing, self-healing, self-recovering. Star just represents a set of properties that you associate with the system that are autonomic. Autonomic means the system can make decisions without human intervention. It is intelligent enough to make those decisions itself. Okay. In a self-healing system, for example, if nodes fail, the system will notice that nodes have failed and it will recover from the failure without having a human having to do anything about it. Okay. That's just one example. Okay, now the typical architecture will have several things in it, and so monitoring, modeling and prediction, and making autonomic decisions are the three things that any of these self-start system would do. To make autonomic decisions, first you have to observe the system. The system is observing itself. Okay, it's trying to monitor itself, saying what might be happening inside the system that requires corrective action of some sort. So you have to have monitoring, and then the monitor data is analyzed to figure out, is the system operating normally, are there abnormal conditions, does the system need to take any action. Yeah, so that's the analysis and the modeling step. And then once you figure out that something has to be done, then you will make that decision autonomically. Okay. In this case, the specific example that is actually shown here is one where the web server, okay, is autonomic, and it can scale its capacity automatically as the load on that web server rises. Okay. So what you are going to do is you are going to monitor the web workload, the HTTP request rate. Then you are going to analyze it to see, for that request rate, do you have enough server resources? Are the servers heavily utilized? Are they saturated or approaching saturation? If you see that the load is rising and you are going to hit your capacity limits, then you will take corrective actions, which in this case is adjust allocation or add more servers or add more capacity to your website so that it does not start terminating requests without serving. Okay? So we'll come back to all of this again later. That's just one example of how autonomic systems work. Okay, so this falls under this category of self-managing systems or autonomic distributed systems. Okay, any questions on this? All right, so now I'm going to switch gears and talk about processes, threads, and scheduling, which is the next chapter in the sequence. Okay, so today we are going to do a quick review of processes and process scheduling. That material is typically covered in an undergraduate OS class. Okay, so if you have that background, bear with me. I just want to go through that quickly so that if somebody is forgotten or does not have undergraduate OS background, you will be brought up to speed quickly. Okay, then we'll talk about threads and their scheduling. Okay, again, and then once we are done, next time we'll talk about things like multiprocessor scheduling, distributed scheduling, and so on. Okay, so we'll only cover the first two bullets today. The rest of it will be covered in the next class. So like last time, we'll have 3 or so modules or 3 or so parts of the lecture. First, I'm going to talk about processes, and then I'm going to talk about threads, thread management, and at the end we'll talk about how to schedule threads and how they map to different architectures and so on. Okay, so let's start with the notion of a process. I assume all of you know what a process is. Okay, simply put, it's a program in execution. A program is a piece of code that you write. When you run it, that gets instantiated as a process by the operating system which runs your program. Okay? So processes basically are tracked by your OS kernel, because the kernel is going to manage all aspects of that process, which includes how much memory to give it, when it runs on the CPU, and what files it has open. All of that is tracked by the OS kernel. And in typical undergraduate textbooks, you will find this term called a process control block, or the PCB. That's basically referring to the kernel data structure that is tracking all processes. Okay, that's all there is to it. Okay. Now every process is going to have an address space. Okay, the address space is essentially the region of memory that process resides in. Okay, and typically that region of memory is going to have the code for that process. Okay. So it's going to have the code, it's going to have the space for all of the data, which is going to include the stack and the heap. Okay, so a very simple picture of what a process looks like, okay, is one where you have this logical layout, memory layout of the process. You have what is called the code or the text segment of the process. This is where all the machine code resides. That's where the binary instructions for that process reside, which are generated from whatever code you write, okay, by the compiler or an interpreter or whatnot. Okay, and then there is the stack segment, and then there is the heap segment. Okay, all dynamically allocated memory sits in the heap. All statically allocated memory sits in the stack. Okay, and the heap will grow upwards and the stack will grow downwards. Yeah, that's like a typical layout of a process. Because in this case, the process has three segments. Segment is a region of memory. Is a text segment, also called the code segment, the stack, and the heap. And you can have many more, like shared libraries and others that are linked to that process. Okay, but at least three. Okay, that's the layout of a process you should have in mind, because we are going to return to that very soon when we talk about threads. Okay. All right. So that's the address space of the process. Now, typically, over the lifetime of the process is going to do various things, which causes us to make various state transition. Okay, when a process starts, okay, or starts executing, it will start in what is called a new state, which indicates this is a newly arrived process. Okay, in this case, the OS is just setting up the data structures for that process and loading it into memory and so on. Okay. Once it has done that, the process is going to be ready for execution. Ready simply means that it is ready to run, but it hasn't actually been scheduled on the processor to execute. Okay? And the CPU scheduler at some point will choose this process for execution, at which point it will actually start running. That's the run. You go into the run state. Okay, and then from the run state, you might go back to the ready state. Okay, if you basically a quantum or time duration expires, or you might go to the wait state if you do I/O. Okay, so the I/O causes the process to block, so you will block in the wait state. Once the I/O is completed, you will go back to the ready state. Okay, and then once you are done with execution, you will basically go to the finish state. Okay, that's a very simple state transition diagram of that process. So essentially, it spends most of the time cycling between run, wait, and ready. Okay, so you basically, depending on whether you're executing, you're blocked on I/O, or you're just waiting for the processor. Okay, you will be in one of these three states. Then once you finish, you will basically go to terminate. Okay, is that clear? Okay, so essentially the job of the CPU scheduler, which is part of the OS kernel, is to look at all the processes that are in the ready state, okay, and pick one for executing next. Okay, there will be several processes that might be in the ready state, and if you have a single core, then you will basically have to pick one of them and execute it next. Okay, and it will give you given a time slice. You will run for the duration of the time slice unless you do an I/O before your time slice ends. In that case, you give up the CPU, go into wait state. But if your time slice ends, you will use up the time slice, go back to your ready state. CPU scheduler will run. It will look at again all of the ready processes and pick another one, and so on and so forth. Okay? So the job of the CPU scheduler is to look at what is called the ready queue. Okay? The ready queue is essentially a list of all the processes that are sitting in this state, and then pick one for execution. And depending on what policy you choose, you will get different CPU scheduling algorithms. Okay? And here are several that we have listed. I'm not going to go into them today. Okay, there's round robin, which says you just round robin across all the processes in the ready state. The shortest job first, that says pick the shortest job to run of all the jobs that are in the ready state. There is first come first serve or FIFO policy. There is a lottery scheduling policy, which is a randomized policy, which says randomly pick one of those processes based on this notion of a lottery, which we don't need to go into here. Okay, and so on and so forth. Okay, I'll talk about some more sophisticated ones in a little more detail. These are some simple policies that can be used by a CPU scheduler. Okay, and there are different properties, and the properties that you typically want to achieve, okay, by scheduling these processes is get high throughput, try to get high CPU utilization, get low turnaround times, get short response time, be fair to a process, not starve any processes, and so on. Okay? So these are all good things for an OS kernel to achieve as part of CPU scheduling. Okay? The thing to keep in mind is that there is not going to be one policy that can optimize all of them simultaneously. Okay? Each of these techniques will try to optimize some or one of those things. Okay? And it often comes at the expense of other things. If you try to make one thing better, because you have finite resources, it's going to come at the expense of making something else worse. So you really have to decide as an OS kernel designer what kinds of goals do you want to have for your system and pick a CPU scheduler that achieves those goals. Because although all of those goals that I've listed here look like good things to go for, you cannot get all of them at once. Okay? You have to make some trade-offs when you design your system. Okay? Any questions here? All right. So now I'm going to give a little more detail, then talk about CPU scheduling in a little more detail there. So if you look at the lifetime of a process, I said it essentially transitions between ready, run, waiting, and so on, and it will cycle through these states before it finishes. Okay? What that should also tell you is that the typical lifetime of a process, you will see that it will have different phases. Okay? In some phases, it's doing CPU computation. Okay? In other phases, it's doing I/O, where it's basically trying to read or write data to or from disk. Okay? And it may cycle between these phases over time. Okay? So over the lifetime of a process, the process might transition from being CPU bound, where it mostly spends time on the CPU, to being I/O bound, where it spends most of its time doing I/O, back to being CPU bound, and so on and so forth. Okay? There are things that are called CPU bound processes, which means they predominantly need CPU cycles. They don't do a whole lot of I/O, they just compute a lot. Okay? And then there are I/O bound processes, which say the process predominantly does I/O. It doesn't do a lot of computation. It might do short amounts of computation, go back to doing I/O. So you can have jobs that are predominantly one or the other, but most applications will go through different phases over its lifetime. Okay? When you start a process, it might read a bunch of data from disk. Okay, that's being I/O bound, and once the data is in memory, it might start doing some computation, that becomes CPU bound, then it writes out some results, that becomes I/O bound again. Okay, so you will have these cycles going back and forth. Okay, and what this slide is showing, really, there's a lot more detail there than you need to know, is that if you actually examine the periods of time the process is computing, which is what we call a CPU burst, you will see that the duration of this burst, okay, have this property. Most CPU bursts are short, but there are some that will be very long. Okay, which means over the lifetime of a process, you might have several short periods for which you will do computation before starting to do I/O. Okay, but there will be some periods where you have a long burst of I/O where you're just doing computation with no I/O at all. Okay? So most of your CPU bursts will be small in size, and there will be a few that are very long in size. Okay? And this is the property that we are going to exploit in a little bit to understand how to do scheduling. Okay? Now there are several researchers who have actually studied the statistical property of CPU bursts and try to fit distributions on them and so on, and typically it is assumed that if you look at the duration of CPU bursts of all the processes in your system, you will see that it follows what is called a hyper exponential distribution, which is meaning it looks like this. Okay, there is basically a peak that is very close to zero, and then there is a long tail that follows it. Okay? We don't need to go into why it is hyper exponential or what, if you don't know what hyper exponential is. Yes, this is an exponential distribution, 1 minus e to the power mu x. This is an hyper exponential distribution where there are two exponents. Okay? But we really don't need to go into this here. What you need to understand is that there will be many processes that require short amounts of computation time, short CPU bursts before they go back to doing I/O, and there are some processes that need a lot of CPU. There are long bursts. Okay, that's really what we need to keep in mind for what's coming next. Okay, any questions here? Okay, so now let's talk a little bit about more sophisticated schedulers. In particular, we are going to look at prioritized schedulers. In prioritized scheduler, it's assumed that your process actually is given a priority. Okay, and essentially the CPU scheduler will always pick the higher priority processes first to schedule before it schedules any lower priority processes. So now you have what are called priority queues, which is also what is shown in this very small figure here, where there are 3 queues, okay, of different priority levels. Okay. So the CPU scheduler will always start with the highest priority non-empty queue. So you'll start at the top. If that queue is non-empty, you will basically pick a process from there to schedule. And there you could use any policy. Let's say we'll just use round robin within each queue. Okay. So every time you'll start with the highest priority queue that is not empty and do round robin. And once that queue empties, you'll go to the next highest priority queue and so on and so forth. Okay. That's what any priority scheduler would do. It schedules jobs based on priorities. Okay. Now in many systems you can assign hard and static priorities to certain jobs. Okay, and those processes or jobs will always run first before running other jobs. Okay. Examples of this would include the OS kernel itself, which could run at higher priority than user processes. Okay, because if the kernel needs to do something, you want to give it priority over some user application that's doing some routine task from a CPU scheduling perspective. Okay. And there are many other kernel tasks like pay, memory swapping, and real-time tasks and so on. Okay. So this could all be arranged using prioritized scheduler. Okay. Now interestingly, many OS schedulers also use this notion of priorities to schedule user tasks, normal applications. Okay. And in this case, they will actually use dynamic priorities. Okay. The priority of a process will change over time, which will determine when it gets scheduled and how much CPU time it receives. Okay. And this class of schedulers is called multi-level feedback queue or MLFQ. Okay. Again, something you may have encountered in an undergrad class, but let me explain what this is. Okay. So I'm going to draw another figure, that figure there that we have, I'm going to reproduce here. So we'll assume that your scheduler has 3 queues. And this is your CPU. Okay. So this is, let's say, the highest priority level 1. This is the second highest priority level 2, third highest priority level 3. Okay. So what will happen in this case is when new processes arrive, they will join because you don't know anything about the process. By default, you will put it in the highest priority queue. Okay. Whenever the CPU time slot ends and the CPU becomes idle, your CPU scheduler will run. It will start at the top. If that queue is empty, you will go to the next one and so on until you find the first non-empty queue. In this case, the very top queue actually has a job, so you're just going to pick that job and run. Okay. So now once a job has actually taken a time slot on the CPU, you are going to decide what to do with it based on what it did during its time slice. Okay. Specifically, if it uses its entire time slice, okay, you are going to drop it 1 priority level. On the other hand, if in the midst of its time slice, it started doing some I/O and it did not use its entire time slice, you will first put it in the wait queue, let it finish its I/O, but when it rejoins, you will increase its priority level by 1. Okay, so the rule we are going to follow is whenever a process gets scheduled from any queue, let's say a process got scheduled from this queue, okay, and it got a time slot on the CPU, you will observe what it did during the time slot. If it used its entire time slot, okay, it will go back to the ready queue, but you will drop it 1 priority level. In this case, it will drop from 2 to 3. Okay. But on the other hand, if in the midst of its time slot, it did some I/O, then it will rise in priority. Okay, that's the simple rule we are going to follow. Is that clear?
So what is the reasoning behind this?
Yes, that's good. That was going to be my question. So why would you do something like this and what does it achieve? Okay, first let's ask the question, how do different types of jobs get treated in this system? Then we'll see is that the right thing to do or not. Okay, let's take a CPU bound job. Okay, by definition a CPU bound job is a job that needs long period or runs has a long CPU burst. It runs on the CPU for long periods of time. So if you give it a short time slice, what is it likely to do? Is it going to finish its time slice, or will it give up its time slice in the middle due to I/O? Okay, so it's going to, with high likelihood, finish its time slot, use up all the cycles that were given to it. What will happen as a result of doing that in terms of where it lands in these priority queues?
It keeps going down.
Okay, so every time you run it, it's going to keep falling because you use up the time slice, you'll keep falling in priority. Okay, so your CPU bound jobs are going to fall and end up in the lowest priority queue. Okay, now take the other scenario, which is I/O bound jobs. Okay, so I/O bound jobs, regardless of which queue they are in, if they start doing I/O, okay, with high likelihood, they are not going to finish their time slice. They run because, as I said, this is where some of what I said previously comes in. Most of these bursts are very short. Okay, those actually are bursts from I/O bound jobs. So those are the jobs that will not take their entire time slice. They run and then some number of instruction, they hit an I/O instruction, they basically give up the CPU, go back to doing I/O. Okay, so what does happen as a result of that from where they land in your priority queue? Okay, they have to rise because our rule says if you do not use your time slice, you rise in priority. Okay, so in this system, you will see that any task that starts doing I/O will naturally rise up in priority, and any job that is doing a computation will fall in priority. So all I/O bound jobs are actually going to be in the highest priority level. All CPU bound jobs are going to be in the lowest priority level. Okay, now you are just doing prioritized scheduling. Okay, so what does this tell you about how we are treating I/O bound and CPU bound jobs?
They're trying to give more time to I/O bound because they haven't spent all of that time quantum, and so they will spend more time to finish their time quantum.
Okay, so you are going to give more time. You are actually going to give more priority, not necessarily more time. Right? So,
time quantum and
okay, so you are giving more priority, higher priority to I/O bound jobs. Anything else?
Generally, the I/O bound jobs are something which are on the screen and user doesn't want any sort of lag. And the CPU bound jobs are something which is like the background processes, which the user doesn't really care as of now, but can be scheduled later. So
Okay.
lag would decrease.
Okay, so you are saying why should you do it? I was simply asking what happens. Okay, does it make sense? And what you said is right, but we'll come back to that. Okay. Yes.
Because you would want to give more room for processes that have short CPU bursts than long CPU bursts. When you do round robin, more of those processes get scheduled.
Okay, so that is an interesting observation, and that is really where we are going. So what you should realize is in this case you are going to favor I/O bound jobs over CPU bound jobs because I/O bound jobs are getting higher priority. That's the first thing. Okay. Second thing that you have to ask is why does that actually make sense? Okay, and that is what was observed just now. So if you have one I/O bound job and one CPU bound job, okay, if you are not treating them any differently, okay, if you actually schedule the CPU bound job first, okay, it's likely that it will use up its entire quantum, and the I/O bound job is just waiting for a turn to run, and then it will go next, but it has waited for the first quantum to have gone by. Okay? But if you schedule them the other way around, which means you schedule the I/O bound job first, it will run for a short period of time, some fraction of that quantum, and then go back to doing I/O. Okay. Now the amount of time the CPU bound job waits is now much lower than the amount of time the I/O bound jobs waited. Okay. So essentially by doing this you are reducing the overall time you have to wait in the system, which means you let the small jobs, which are your short bursts, go by quickly, and then you resume executing the longer CPU bound jobs. Okay. So that you basically reduce the overall waiting time. Yes.
But if you prioritize input output jobs, then won't we have a higher overhead because we are switching the control between, like say, monitor and CPU. Like all the higher priority jobs are all input-output jobs. So
Okay, so question is there any harm in scheduling the input, output or the IO bound jobs? Okay, so you have to realize that we are not prioritizing the IO itself. We are prioritizing the CPU time spent by an IO bound job. So that's where it's actually doing computation. IO is dealt with. All you are saying is if a IO bound task becomes runnable, it's in the ready queue, it needs a short amount of CPU to make some progress and it will go back to doing IO. Why not let it run for that short period and go back to doing IO? Then we have the rest of your time quantum to run or cycles to run your CPU bound job. That's the rationale. Okay? This technique will actually optimize wait times in the system. Okay, it will reduce the overall waiting time by doing so. Okay, that's the main rationale for why you want to do this. Okay, it used to be the most common CPU scheduler that was used in operating system kernels. Okay, with the advent of multi-core things and so on, this is not used as much anymore, but that is how it began. Okay, yes, your question there.
So if a process is there, suppose it has t times that it gets to spend for the CPU, and after t by 2, gets it gets an interrupt. It has to read like lots of file. What happens that at that time isn't this CPU like not doing anything? So the CPU cycles are getting wasted, right?
Okay, question is if there is a job that runs and in the midst of its quantum it gets an interrupt, what is going to happen? Will the CPU cycles get wasted? So that is exactly what I had said. If you actually either get an interrupt or you start doing IO, you will give up the CPU. You will go into the wait queue and your IO device will service your interrupt or will service your IO, and the CPU scheduler will pick another job to run. You are not going to keep your CPU idle because some job is decided to do IO. Okay, that's how any scheduler works. Okay, if you are in the midst of your quantum, you get an interrupt or IO, you will essentially cause that job to give up the CPU, and it will go back to servicing whatever interrupt it had or IO, and you get some other job to run. Okay? Does that answer your question? Okay. Anything else? Yes.
Is there anything to worry about in like how long each time quantum is? Because like if you have like very long ones, then maybe this won't work very well.
Okay. So question is how long should the time quantum be, and should we worry about it? So that's the last piece of this scheduler that I had not yet mentioned, which is I said that the queues have different priority levels. Okay, and I said within each priority level you have time slots and you schedule them in round robin, but I didn't say anything about time slices. Okay, and as it turns out, the higher priority queues here have shorter quantums and the lower priority queues have longer quantums. Okay, so if the quantum duration here is 1 millisecond, okay, it will actually be double 2 milliseconds, and this will be 4 milliseconds and so on. Okay, you might have more than 3 queues. Okay. So what this also says is because your CPU bound jobs are at the bottom, they get longer quantums. There's no point needlessly context switching because they can run for long periods of time. You reduce your context switch over it. On the other hand, because the jobs in the highest priority queue are likely to be IO bound jobs, there is no need to give them long quantums because they cannot even use short quantums. Okay? So the quantum duration actually goes up as the priority level decrease. And that is also an artifact of what kinds of jobs land up where and how to optimize context switch overhead. Yes, question there.
I'm confused now, right? So I assume that a process can have both IO bound things and CPU bound things. So if you shift, maybe a process is going through an IO phase, and you shift it up, and then it requires some CPU bound phase. So isn't it a big disadvantage?
Okay, that's a good question, which is since processes can switch between being IO bound and CPU bound, which is what I had shown on the previous slide, labeling them as IO bound or CPU bound might be to their disadvantage because their behavior changes over time. Okay? The nice thing about this scheduler is it's actually dynamic priorities. Okay, it adjusts as the behavior of the process changes. If you are CPU bound and you suddenly start doing IO and you are at the bottom queue, you will start rising. Okay, so in a few quantums you will actually reach the top. Okay, and the vice versa. If you are doing a lot of IO and now you start doing some computation, you will start falling. Okay, so this the CPU scheduler has not statically labeled a job as IO bound or CPU bound. It is observing every time that job runs, what did it do, and it's adjusting your priorities accordingly. So if you change behavior, the CPU scheduler will treat you differently. Okay, yes.
So if a job is CPU bound and so suppose the slot allotted to it was not enough, so the time got over, but it didn't finish doing the job, and it's also not doing it. Then what happens to the?
Okay, question is what happens if you use up your entire time slot? That is how scheduling works. You just go back to the end of the queue and wait for your turn. Again, you're doing round robin within each queue. Right? So you will basically go back to your end of your queue. Okay, so let's move on because we have several other things to cover. Okay, so now we are going to actually talk about threads. Okay, all this was just a recap from traditional process-based scheduling, typically material from undergraduate class. Okay, but this is now we'll move from processes to threads. We are going to switch gears a little bit. Okay, so to understand what are threads, I'm going to point back to this picture of a process. Because a process essentially has a code segment, it has stack, it has heap, of course it has registers and so on, but I didn't show those things here. Okay? And when a typical process executes, it's basically executing sequentially through the code segment. Okay? So it will basically execute an instruction. Okay, then it will go fetch the next instruction. Unless there's a branch or something like that, it will start executing sequentially. Okay? So there is one stream of execution through that process where you are executing one instruction at a time, stepping through your code that you have written. Okay? So a traditional process has one stream of execution that is woven through it. Okay? Now if you generalize it, you will get the notion of a thread where there are multiple streams of execution that are woven through the same process, what used to be a process. Okay? So what that means, okay, is we are going to generalize this. I'm going to erase this here. Okay, let me draw this picture again. Okay, so you have, let's say, your code segment, and just for simplicity, I'm going to show source code. You should realize this machine code is what's executed, not source code, but just to keep it simple, I'm going to show you. So here's a simple piece of code which has a main function and another function foo. Okay, just one program has two. Now if you had a single process, you have to start at the top of main and it will execute this. Somewhere in here it might jump to foo, execute that, come back and so on. That's how a normal process would execute. But if you have multi-threaded code or you have this notion of a thread, then you could be executing some part of this function and then at the same time you have another thread that is executing some other part of that code within that process. Okay, so you might have one thread that's executing code in that function foo, another thread that's executing code in that function main, and there could be many more threads that are executing arbitrarily different parts of that code all at the same time. Okay. Now each of these threads is going to get its own stack, because when you are in a function you might have variables on the stack and so on. So instead of one stack that you had in that original process, you are going to have more than one stack. So you will have stack for thread 1, you will have another stack for thread 2, you will have a stack for thread 3 and so on, and then there is a common heap that is globally shared. Okay. So each process gets its own stack, or rather each thread gets its own stack, and then the heap is all shared. Heap is just one large pool of dynamically allocated memory. Okay. So now you have actually concurrent execution of your code. Okay, you have written some function code which has, let's say, more than one method or objects or whatever it is. There are different parts of your code are being concurrently executed by different threads. They are all within the same process. So you generalize the notion of a process where only one statement is being executed at any given time to k statements being executed at any given time if there are k threads in your process. Okay? So there are essentially k things getting executed. Is that clear? What is the thread? Okay, so thread basically, so you have a flow of control through an address, through the address space. Each address space can have multiple concurrent flows. Each flow of execution is called a thread. Okay, each thread has access to the entire address space. Okay, this is thread T1, this is thread T2. They have access to the heap, they have access to all global variables, they have access to their local variables and so on. So they all share the same memory space. Okay? If you have two processes, they have disjoint memory spaces. Each has its own space in memory. If you have two threads within the same process, they share the entire memory of that process. Okay, that's the important thing to keep in mind. Okay, so you have access to the entire address space. Essentially, you are going to get concurrent execution. Okay? If you have a unicore system or a uniprocessor system, you are now going to start scheduling threads, not processes. Okay? Whatever I said previously about multi-level feedback queue or round robin, there you are picking the next process to schedule on the CPU. Okay? Here you are going to do something more fine-grained. You cannot just pick a process because the process has multiple threads in it. You are directly going to pick a thread within a process and schedule it. Okay? So essentially now you are scheduling threads. And if you have multi-core systems, meaning you have more than one core of your machine, you might get what is called true parallelism, because your CPU scheduler can say run thread T1 on core 1 and run thread T2 on core 2 both at the same time. Okay? Then you get true parallelism, where you actually your code is executing on multiple cores at the same time, so you'll get true speed up. Okay, in a single core system, you will basically switch between threads, so you will have different threads making progress at different times. It will look like the threads are executing in parallel, but in fact they are executing concurrently. Okay, one at a time. Yes, question there.
Is each thread treated as its own process, or are they all on the same priority level?
Okay, is each thread treated as its own process. So from a kernel's perspective, and we'll come back to what the kernel can see within that process, but for now let's assume threads are visible to the OS kernel. Okay? The threads are visible to the kernel. The kernel knows that there is this process P, and it has in this case two threads in it. So from a CPU scheduler's perspective, it's actually scheduling threads directly. It will say I will schedule thread T1 of process P. Okay? Rather than saying I'm going to schedule that process. So that's basically how you are making scheduling decision. It's not that the thread is a different process. Both those threads actually share the same address space, as you can see. Okay, so from the kernel's perspective, there's one address space, there are multiple things executing within that address space. Okay? Alright, so of course you need to do synchronization if you have concurrency, but we'll get to that at some later time. So here's another picture that shows essentially that in a slightly different way. So you will see that there is essentially, these boxes are essentially the threads. You will see that each thread not only has its own stack, it has its own program counter, which points to which statement or which instruction I'm executing from that process. Okay? Because each thread is executing a potentially different part of the code. Each thread needs its own program counter, it needs its own set of registers, and it certainly needs its own stack. Okay? But the rest of the process is all shared. The code segment is shared, the heap is shared, global variables are shared, and so on and so forth. Okay, is that clear? Any questions here? Okay, so we are going to see some examples of where you can use threads or why you should use threads at all. Okay? So there are many different reasons we can actually use threads. One of those many reasons is advances in hardware technologies has resulted in machines that have lots of cores. Okay? Your phone will have 4 cores now. Okay? Your servers may have 64 cores because there are lots and lots of cores. Okay? If you write your processes as single-threaded application, the traditional process is also called a single-threaded process because there's only one thread of control. Okay, if you write it as a single-threaded, if you write all applications as a single-threaded process, it is much harder to take advantage of lots of these processing resources, because at most that process can run on only one core at a time because it has only one thread. Okay? So if you have 64 processors, there better be 64 processes that are all ready to run that can all be scheduled on those cores independently. Okay? But on the other hand, if you write your code or your processes to have multiple threads in them, each of those threads can be scheduled independently. You can make better use of your cores on your machine because you can use parallelism within your process to actually take advantage of parallel execution and lots of cores and lots of CPU power. Okay? So this has become more natural way to write applications, simply because most systems that you buy today, general purpose computing systems, just tend to have more than one core. Okay, so this is a good way to exploit the presence of multiple cores. Okay, that's one. The second thing is there are some inherent advantages of threads. Okay, threads are more lightweight than processes to switch. Okay, so if your CPU scheduler runs, it switches from thread T1 of that process to a thread T2 of that same process. Okay, the context switch overheads are smaller because all of the memory is the same. You don't need to save memory state and reload new memory state and so on. Okay, so thread context switches tend to be cheaper than process context switches. Of course, if you switch from the thread of process P1 to a thread of a different process P2, you will incur a higher overhead because now you are switching both threads and processes. Okay? But switching between threads of the same process is much more lightweight, which you can take advantage of. Okay? Some context switches will be very cheap, which means there's less bookkeeping to do. You'll get more time to run, less time to do switching. Okay? And then there are many other advantages. I'm going to show some examples. Okay, also thread creation, thread deletion, all of this is much cheaper than process creation, process deletion, and so on. Because when you create a new thread within a process, you don't need to set up any more memory because the entire address space is already loaded in memory. Okay? You just need to create some additional data structure which says here's a new stack for that process and maybe here are its set of registers. That's it. You don't need to go and load up the entire process again from memory or anything like, or from disk. Okay, so it's much cheaper to do thread management and process management. Okay, so there are some inherent advantages here. Okay, and what this slide is showing you are some comparisons between traditional process-based applications and threaded applications. Okay, so if you have a single-threaded process, okay, there is no concurrency. There's only one thread of control. No concurrency, no parallelism. Furthermore, okay, if that process makes a blocking system call, it does any IO or any interrupt, the entire process is blocked. The whole process goes into the wait queue, which is what I was explaining earlier. Okay. Now, in the case of a multi-threaded process, okay, they can also make IO instruction, they can also make blocking call, but if a thread does that, only that thread goes to the wait queue. All the other threads of that process are still runnable and your process as a whole can continue to execute on the CPU. Is that clear? Okay, so if some threads of a process block, the entire process does not need to block because other threads remain runnable. You can actually execute the other parts of the process, okay, other threads in the process rather. Okay. Unlike in the single threaded process, nothing can happen once you have an IO instruction. The whole process is going to block, even if there's other work to be done, okay, until the IO is done. Okay. So now between these two models is this middle model which is called the finite state machine model. It's also called the asynchronous IO model, okay, or sometimes also called the event based model. There are many names that are given to this model. Okay. What this does is it takes a single threaded process and tries to put some concurrency in it. Okay. And the way you do this is you make all IO operations non-blocking. Okay. You use something called non-blocking IO, which means you'll issue an IO instruction, okay, and the IO instruction is sent off to the kernel, but the process as a whole is not going to be blocked. It can continue execution. Okay. And later on when the IO finishes, there's an interrupt or an event raised saying your IO is done, so you asynchronously go and service your IO response. Okay. So you still have single threaded process except that you return it in a non-blocking fashion, which means if there is any IO, the process will not block, unlike in the traditional case where you just use standard blocking calls. Okay. So if you write your application this way, okay, you are certainly not going to block if there is any IO instruction. You can still continue to run, which is sort of like what threads do, because if some threads block, the rest of the threads don't block. They can continue to run. Okay. So you are getting some advantages of threaded application, okay, but you won't get all of the advantages. You will get concurrency, but you will never get true parallelism. Yeah, because at the end of the day, it's still a single threaded process which is just doing non-blocking IO. If you have more than one core, it can still run on at most one core at a time. Okay, so you will never be able to run on more than one core because it's essentially still at the end of the day a single threaded process, which is why it says you will get concurrency. Here you get true parallelism. Parallelism means concurrency, but I'm actually executing in parallel. This just says it looks like I'm executing in parallel, but I'm just being concurrent. Okay, so there's a subtle distinction between the two. Okay. Now from a software engineering perspective, okay, it is much more complicated to write event-based applications or applications with asynchronous I/O, because a lot of event handling to be done, a lot of handling of asynchronous I/O and so on. It's much easier to write your application either as a single-threaded process or as a multi-threaded process with blocking calls, okay, because that is what you are used to. If you say read some data from a file, when that read call returns, you expect that the data is there. In a non-asynchronous I/O environment, your read will return, but the data hasn't yet arrived. You just continue execution, and later on you have to process the read. Okay, so it's much more complicated to write. Yes, question?
So this finite state machine, they run in, they talk about this kernel space level like threads, right? Like it has a blocking thing, so it will send to kernel, and kernel will schedule the thread. In the single-threaded process, I understand that both user-level threads and kernel-level threads will behave in the same way. But with finite state machine, is it like are there user-level threads also? Like if we use a user-level library, like as
So I will come to user-level libraries. This has nothing to do with threads at all. Finite event-based is a single-threaded process. You're not using threads to begin with. So it doesn't matter what kinds of threading library is there, because you're not using it to begin with. All you're doing is you're writing your application using non-blocking I/O. Okay? Whether you use user level or kernel level threads, which we will cover shortly, only applies to a multi-threaded process. It does not apply to the first two, because there's only one thread there. So it doesn't matter.
so finite state machine will also have one thread, but if it is like working, suppose some operation it needs some access, some I/O operation, then it sends to the kernel that and does not it sends it, and it is asynchronous, means it is not stopping its function. After that the operation I/O operation is done, it gets an event. Who is doing that I/O operation?
Okay, question is who is responsible for doing I/O? In any of these models, all I/O is always done by the OS kernel. Okay, this requires you to at least have some basic understanding of how kernels work. Okay, whenever a process executes, it doesn't matter what those models are. I/O is supposed to be privileged operation. So I/Os are always done through system calls and handled by the kernel. Processes never actually do I/O, they just issue I/O requests, and they're always handled at the kernel level. So in all of these models, whether it's blocking or non-blocking, okay, the I/O actually is handled by the operating system kernel. Okay, so that much is something you should have a good understanding of, is how is I/O handled, who is handling that I/O and so on. Okay, but typically it doesn't matter in this case, because it's all going to be done by the kernel. That makes sense? Okay, any other questions? All right. So two examples here. One is a client or a web browser rather, which is a client, and then we'll look at web server, how to write them in a multi-threaded fashion. Okay, now if you take a standard browser, if you think about all the tasks that the browser has to do, okay, the browser has to have a user interface. That's how users interact with the browser. Okay, now suppose that the user clicks on some link, okay, then the browser has to actually make a connection to a server somewhere, an HTTP connection. Okay, and then it has to wait for the server to send the data back. Okay, once the data comes back, if it's an HTML document, you have to pass that HTML document. The HTML document has images embedded in it. You have to make connections to fetch all of those images, and so on and so forth. Okay, so typically when you have any web browser, it has to perform these multiple tasks. Okay, now you could say that if you want to write that browser in a multi-threaded fashion, you have certain threads performing certain functions in your code. Okay, you might have threads that are just responsible for UI interaction. They're just doing rendering, they're waiting for user event, mouse clicks or user typing, and they just process that. That's all what those threads will do. There will be other threads that are responsible for network I/O. All that they do is they just make HTTP connections and download data. Okay. There are still other threads that might be processing data that has come from a server, HTML parsing, HTML processing and so on. still other threads that might be doing rendering of images. Okay, once the image comes, you have to display it on the screen, so you can do image rendering and so on. Okay. So you can write your application, in this case the web browser is your application, in a way where you have certain tasks that are dedicated to certain threads or certain groups of threads. Okay. And then if you have tabs within your browser, each tab could also have a set of threads associated with it. Each of those do all of those things. Okay. So you can see how you can take this simple example of a web browser and take all of the pieces that you have within a web browser and associate threads to perform those tasks independently of other threads. Okay. And again, as I said, if you have multi-core architectures, then those threads can actually execute in parallel and get you good responses to whatever images or other things you're downloading. Okay. That's an example of a multi-threaded client. Here's an example of a multi-threaded server. In this case, I just picked a web server, but there are many servers that do exactly the same thing. Okay. Typical web server, also called an HTTP server, is going to have the following function. It's going to listen on port 80, which is the HTTP port for your web server. Okay. Typically, your web service listens on port 80 of on your machine. Okay. HTTP requests will come on the socket port. Okay. There will be some thread that's listening for those requests. They will take the request and then it will hand it off to one of the worker threads, saying, here, go process this user request. That worker thread will then take that HTTP request, do whatever needs to be done, okay, and produce a response and send it back. Okay. So that's what is shown in this picture, where you see this thread called a dispatcher thread. All it is doing is waiting for requests and handing those requests to one of the worker threads. And there's a pool of worker threads. You will see 3 worker threads here. All that they're doing is they're waiting for a request to be given to them. Then they go off, process that request, produce a response, and then they become idle again, wait for the next request. That's all that they will do. Okay. So that's a standard way of writing a multi-threaded server, where you have a dispatcher and a set of worker threads. Okay. Worker threads actually do the work. The dispatcher is simply assigning work as new requests come. Okay. Requests are work in this case. They get assigned to worker threads. Okay. And then there are architectures. In this case, if you have an Apache architecture, you can actually start with a small pool. Okay. You can ask how large should the pool of worker threads be. Okay. You should realize that that pool determines the concurrency or the parallelism of your system. Okay. If your number of worker threads is 3, okay, and it's static, that means that your web server in this case can service 3 requests in parallel. If a 4th request comes, it will have to wait because there is no worker thread that is idle. They are all processing requests. Okay. So the larger your pool of worker threads, the greater is going to be the concurrency you can achieve, because those many requests can get serviced without having to wait. Okay, is that clear? So then you should ask, how large should your pool be? Yes. Okay, first I have to ask, you have to answer my question, then you can ask the question. Is there a question about my question, or are you going to ask a random other question? Okay, we'll come back to your question. Are you going to answer the question or something else?
Maybe you should have like some like a factor or 2 more than the number of CPUs.
Okay, so one suggestion is you make it some multiples of the number of CPUs. You had something else?
Based on the workload.
Okay, based on the work. So if you just make it some fraction of the number of cores, if those threads start doing I/O, then all the cores will sit there idle, even though there may be requests coming. Okay? So typically you shouldn't tie it, there should be some relationship to how much resources you have in the system. In this case, those resources are cores. But a better way to think about it is to decide how many requests are going to come concurrently. If in the worst case you have n requests all come at the same time, you better have n client worker threads, or server worker threads rather, that can process them concurrent, so no request has to wait. Okay? Now, you may not know ahead of time how many requests are going to come. If you set up a website, how do you know beforehand how many users are going to connect to it in the worst case? Typically, you don't know this information. You will only know this after the fact. Okay, but you have to configure your web server before. Okay, So you can do various things. Okay, you have something to say?
Can we dynamically change the number of?
Okay, we can change the number of threads dynamically. So you can start with some static pool. Either you can make some guess saying, I think it will never be more than 100 and start 100 threads. Okay, but then if you have guessed wrong and you have far fewer requests, then you have lots of idling threads that are taking up resources and wasting memory in your system. Okay. If you are too few, then you will have waiting because you will run out of worker threads and new requests will have to wait. Okay. So any sophisticated server is going to essentially change the number of worker threads dynamically based on the current load. Okay. So if it starts running, it will actually track the number of idle threads. If that idle pool starts shrinking, it will say the workload is going up, more and more threads are busy, it will start creating additional worker threads. Okay. And vice versa, if there are lots of worker threads sitting and not doing any work, it will say there's too little work in the system, there are all these threads idling, it will terminate a few. And it will vary this dynamically so that it neither ever runs out of worker threads, or if it does, it starts new ones quickly. Neither will it have lots of idling threads sitting there idling and not doing any work. Okay, but let me go back to, you had a question which we deferred. What was your question?
So processes can issue threads. Can threads issue other threads?
Processes can create threads. Can threads create another thread? Is that your question? Yeah. So as far as thread creation or process creation is concerned, okay, there's a system call that you are going to call, which creates a thread. Okay, anyone can call that system call. So one thread can certainly create as many threads as it wants. It has to just call a thread creation function in your thread library. Okay, yeah, yes.
Is it possible to implement the worker strategy using non-blocking IOs and the base models? So in that case, you can set the number of process of threads equal to the number of cores.
Yes, so that's a good question. The question is, can you actually use non-blocking IO for your worker threads? In that case, you will never block, and you only need as many worker threads as the number of cores, because there's one worker thread per core, it never blocks, so you can keep all the cores busy. Okay? That is essentially what event-based servers will do. Okay, we will come back to event-based servers later. Okay, this is simple blocking IO. Okay, if you have event-based servers, you essentially need one non-blocking thread per core, and then you can keep all the cores busy if there are as many requests as the number of cores. Okay, any other questions here? All right, so let me quickly talk about, in a few minutes that we have, the last part of the lecture, which is going to be thread management. Okay, so yes, your question there.
So if you want to have like non-blocking IO, right, that means that IO should not be running on your CPU, right? And that means you should have like dedicated IO hardware.
Okay, so our question is, non-blocking IO means IO will not execute on the CPU. So typically all IO is handled by the IO devices. Whether it's a disk, IO just means that you got a network packet, you want to read some data from disk, you want to write to the graphics card, those are all examples of IO. So all IO is always handled by IO devices, never actually, only job of the CPU is to issue the IO instruction to the IO device through a device driver. At that point, the device hardware will actually execute the IO. That is how all IO will work. Okay, whether it's blocking or non-blocking does not matter. All IO is always handled by the IO device. Okay. Any other questions here? All right. So let's talk a little bit about thread management. And specifically, as part of thread management, it's good to understand how threading systems actually work. Okay, and there are two types. One is kernel level threads, which means that all threads are created, managed with support from the kernel. The other is user level threads, which means the user's library actually deals with it and the kernel does not have anything to do with it. Okay, we'll quickly go through this so you can understand the trade-offs between the two. Okay. So the key issues for us are how expensive is thread management, okay, based on whether it's user level or kernel level, how easy or difficult it is to schedule those threads in either of those scenarios. Okay, how flexible is it from a parallel programming standpoint, and from what are some blocking properties of this kind of model. Okay, so we'll take each of these in turn, user level, kernel level, and look at them. Okay. So in a user level threads world, the entire functionality of threading is implemented in a user library. Okay. The OS kernel neither supports threads nor does it actually deal with threads. Okay, the OS only supports processes. Okay, within that process, you take a library which is written as a user level library, and you just make calls to that library and create threads. So threads are entirely managed inside that user process with no support whatsoever from the kernel. Okay? Kernel does not see the presence of threads in the process. The kernel sees that address space as a traditional process. So all that the kernel will do is it will schedule that process. Yeah. Whenever that process gets scheduled, the user level threads library will run, and it will have its own thread scheduling technique, and it will pick one of its many threads to actually execute. Okay. So the CPU scheduler picks a process. The thread scheduler within that process, within that user library, actually picks one of the user level threads to run, and that's the thread that's going to run. Okay, so scheduling is actually happening at two levels in this case. Kernel level, which is picking a process, and at a user level, which is picking a thread to run. Okay, so kernel is unaware of the presence of threads. Okay, so advantages is, so you do not need kernel support to write multi-threaded code. If you happen to have a kernel that just doesn't support threads, you can still write multi-threaded application. You just need to find the right library and the right programming language and write your application in that library or using that library and the language. Okay? You don't need to change the kernel at all. Okay? So it is very efficient because thread management are all functions calls to the library within the same process. There is no context switching involved. There is no system call involved. You want to create a thread, you make a library call to the library that's part of that process. It will create a thread for you. Very, very lightweight. Okay, so it's very fast creation, fast management of thread, fast switching between threads and so on. Okay. There's some flexibility in scheduling because your thread scheduler can pick an arbitrary different scheduling policy that's independent of the CPU scheduler. Okay. The CPU scheduler says I do multi-level feedback queue, thread scheduler can say I do something else. Okay. And if that is the right policy for the application you're writing, even better. You're not bound by anything that the kernel is doing for you. Okay. And different threads libraries within different processes on the same machine can do different things. Okay. So you can pick the right scheduling policy for your application by picking the right library. Okay. So you're not bound by whatever the kernel does. So those are all good things of user level processing. Okay. The disadvantages are, okay, so the entire process becomes blocking, even though there may be k processes within the thread, k threads within the processes, not processes within threads. Okay, if any thread makes a blocking call, the entire process will block because the kernel doesn't know there are other threads in the process. They're all handled at the user level. Okay, kernel just sees it as a traditional process, so it will block the entire process. There may be other runnable threads in there. It doesn't know, it cannot run them. Okay, so essentially one thread blocks, all threads block. Okay. Threads are going to compete for one another in the user level threads library. It's not as bad of a disadvantage, but it's still true. And the third thing is you're not going to get real parallelism. Again, because you don't know of the presence of thread, the process is going to get scheduled only once. Okay, even if there are 10 threads, you'll only schedule the process on one core at a time. Okay, you cannot schedule it on more than one core. Okay, so those are all disadvantages. I think I have a picture here I'm going to show and then stop. Okay, so here is an example of how a user level thread library works. Okay. So these are processes or processors or cores, the two cores in the system. Okay. This is your OS scheduler. Okay. These are three processes. You will see there's a library schedulers. Okay. And you will see that there are 3 threads here, 3 threads here, 2 threads here, and so on. Okay. So the CPU scheduler will run, it will pick a process. That process will run the library scheduler that will pick a thread. In that case, it's picked this thread. So that thread will essentially run on that processor for that time slot. Okay. For the second core, the CPU scheduler will run and pick another process. Okay. In this case, it picks this one. Okay. And then that library scheduler will pick one of the runnable threads and it picks this third one, and that's what gets to run. Okay. So this is two-level scheduling that's going to occur. Okay. Clearly, in this case, you will see that the OS sees this entire process as a single threaded process because it's just picking a process. Okay, like a traditional. It doesn't see that there are 2 or 3 or some number of threads in there. Okay, is that clear? Okay, so we will stop here. Okay, and if you came late, there is a sheet that's circulating around. Make sure you mark your thing against your name. Okay.